We're asked to find the area of the surface of the semicone z equals the square root of the quantity x squared plus y squared that lies between z equals 3 and z equals 8. If the function of two variables, g of x comma y, has continuous first-order partial derivatives on the closed region R in the xy plane, the surface area can be determined using this double integral here. Before we set up this double integral, though, let's look at this graph in 3 dimensions. The semicone is graphed in blue, the lower plane is z equals 3, and this plane is z equals 8. Our goal is to find the surface area of the cone that lies between these two planes. If we look down on the xy plane, we can view the region R, the region of integration. The region R is the region bounded between these two circles, where we have this larger circle and we have this smaller circle. And again, this is from projecting the cone onto the xy plane between z equals 3 and z equals 8. So going back to our work, let's show how we can find the equations of these two concentric circles that form the region of integration. Remember, these circles are formed from the intersection of the two planes in the cone. So if we substitute 3 for z into the equation for the cone, we can determine the equation for the smaller circle. And if we substitute 8 for z, we can determine the equation of a larger circle. Let's go ahead and show this. If we substitute 3 for z in the equation of the cone, we have 3 equals the square root of the quantity x squared plus y squared. And now to undo the square root, we square both sides of the equation, which gives us 9 equals x squared plus y squared, which we should recognize is a circle centered at the origin with a radius of 3, which is the small circle. For the larger circle, we substitute 8 for z, which gives us 8 equals the square root of the quantity x squared plus y squared. And again, to undo the square root, we square both sides of the equation, which gives us 64 equals x squared plus y squared, which is a circle centered at the origin with a radius of 8, which gives us the large circle. And because the region of integration is the area between two circles, it'll be easier to evaluate the double integral using polar coordinates rather than rectangular coordinates. Remember, in polar coordinates, differential A is equal to r dr d theta. For the next step, let's find the partial derivatives required in the surface area formula. Let's first write z as z equals the quantity x squared plus y squared raised to the 1/2 power. And now we'll find the partial derivative of z with respect to x. To do this, we differentiate z with respect to x, treating y as a constant, and this will require the chain rule. We will have 1/2 times the quantity x squared plus y squared raised to the power of 1/2 minus 1, which is negative 1/2, times the derivative of x squared plus y squared with respect to x, which is 2x. Let's simplify this. 2 divided by 2 simplifies to 1. Let's write this as x divided by, let's move this down to the denominator, which will change the sign of the exponent, and also write it as a square root. So we have x divided by the square root of the quantity x squared plus y squared. Again, this is the partial with respect to x. And now we'll find the partial of z with respect to y by differentiating z with respect to y, now treating x as a constant. So we'll have 1/2 times the quantity x squared plus y squared raised to the negative 1/2 power times the derivative of x squared plus y squared with respect to y, which is 2y. Simplifying, the partial of z with respect to y is equal to, again, this simplifies. Here we have y divided by the square root of x squared plus y squared. And now we have the information we need to set up the double integral for the surface area. The surface area is equal to the double integral over the region R of the square root of 1 plus the square of x divided by the square root of the quantity x squared plus y squared plus the square of y divided by the square root of the quantity x squared plus y squared, differential a. Let's continue on the next slide. For the next step, let's simplify the radicand. We have 1 plus squaring this fraction, we get x squared divided by the quantity x squared plus y squared. Squaring the denominator undoes the square root, and then here we have plus y squared divided by the quantity x squared plus y squared. We do have a common denominator, so we can go ahead and add these two fractions. We have 1 plus, adding the numerators, we have x squared plus y squared over the common denominator of x squared plus y squared. Notice how this simplifies nicely to 1. So this simplifies to the double integral over the region R of the square root of, again, this is 1. 1 plus 1 is 2, so we have the square root of 2 differential a. This simplified nicely, but because the region of integration is the region between these two circles, let's evaluate the double integral using polar coordinates. And again, remember, for polar coordinates, differential a is equal to r dr d theta. So we have the double integral, and then we have square root 2r dr d theta. Now let's go back and look at the region of integration to determine the limits of integration for r and theta. Well, because the radius of the small circle is 3 and the radius of the large circle is 8, the limits of integration for r will be from 3 to 8, and the limits of integration for theta will be all the way around the circle from 0 to 2 pi. The limits of integration for r are from 3 to 8, and for theta are from 0 to 2 pi. Let's evaluate this on the next slide. We first integrate with respect to r. Remember, this is r to the first, which gives us the integral from 0 to 2 pi of square root 2 times r squared divided by 2, or square root 2 divided by 2 r squared. And now we find big F of b minus big F of a, which will give us square root 2 divided by 2 times, when r is 8 we have 8 squared, minus when r is 3 we have 3 squared. 8 squared is 64, 3 squared is 9. 64 minus 9 is equal to 55, which gives us the integral from 0 to 2 pi of 55 square root 2 divided by 2 d theta. And now we integrate with respect to theta, which gives us 55 square root 2 divided by 2 theta. And now we find big F of b minus big F of a, which is 55 square root 2 divided by 2 times the quantity 2 pi minus 0, which is equal to 55 square root 2 divided by 2 times 2 pi. The 2 simplify, which gives us an exact surface area of 55 square root 2 pi, and because this is surface area, this would be square units. And this is approximately 244.3586. So if we go back to our graph one last time, we now know the surface area of the cone bounded by these two planes is exactly 55 square root 2 pi square units, which again is approximately 244.3586. I hope you found this helpful.